Good day, dear students, friends. Myself, Mr. Syed Hassan Kazi, Assistant Professor, Mechanical Engineering Department, Thondara College of Engineering, Gadag. In this video session, let us learn how to solve the problems on different cross-section bars using finite element method to determine the nodal displacements, stresses in each element, and the support reactions. And these problems on bars will come under module 2 of 6th semester syllabus. Let us consider the stepped bar problem consisting of two materials, aluminum and steel, subjected to an axial load P as shown. Now, in the solution for this problem, let us discretize this stepped bar into two elements. Now this is node number 1, locate node number 2 here and node number 3. Likewise, we have two elements and three nodes, namely 1, 2, 3. Now generate the stiffness matrices. Now generate the stiffness matrices for these two elements. Stiffness matrix for element 1, that is K1 is equal to here. The formula is AE by L, that is A1 E1 by L1, 1 minus 1 minus 1 1. The order of the matrix will be 2 cross 2 for each element having two nodes. Now A is the area of the element, E is the Young's modulus of the material of the element, L1 is the length of the element. Now K1 is equal to area of the element 1 given is, that is for the first step 2400, and Young's modulus of the element 1, that is aluminium, 17⁻³ divided by L1, that is the length of the element 1, is 300. Okay, so after calculation we got 56 into 10⁻⁴. Hence okay, 10⁻⁴ you write outside and 56 will be inside. Now write the DOF numbers for reference. That is element number 1 having the DOF numbers 1, 2. You write for reference, that is 1, 2, 1, 2. That is row and column. Now next, stiffness matrix for element 2, that is A2 E2 by L2. Order of the matrix 2 cross 2, that is 1 minus 1 minus 1 1. Area of the element 2 given is 600, that is area of steel material, and Young's modulus of steel material 210⁻⁴. And next the length of the element 2 400 mm, that is given. Okay, now we got, after the calculation of this term, 30 into 10⁻⁴, take 10⁻⁴, the same common as in element 1. That is 10⁻⁴ outside, and inside will be 30. 30 minus 30 minus 30, 30. For reference, you write the DOF numbers for element 2, that is 2, 2, 3. That is 2, 3 and 2, 3. Now come to the global stiffness matrix. Because there are two elements, we have generated the stiffness matrices for two elements 1 and 2, K1 and K2. Now assemble these two matrices to get the global stiffness matrix K. Okay, for that, since there are two elements and three nodes, first you make a grid of that. Hence the order of the global stiffness matrix should be 3 cross 3, because there are three nodes, hence 3 unknowns. Hence the order of the matrix should be 3 cross 3. Hence you make a grid line of 3 rows and 3 columns like this. Now while assembling, you search the DOF numbers, the terms row 1 column 1, that is 1 1. Here 1 1 it is available, that is 56. Next 1 2, here it is minus 56. Here 1 2 it is not available. 1 3, this value, this term is not available in both the matrices. 1 3, that is 0. And next 2 1, 2 1, that is minus 56. 2 1 it is not available here. 2 2, that is 56 here, and next 2 2 here also it is 30. Then 56 plus 30, 2 2, this one. Next 2 3, 2 3, here it is available minus 30. Here you write minus 30, minus 30 here. Next 3 1, it's not available in both the matrices, write it as 0. 3 2, that is minus 30, it is minus 30. 3 3, that is 30, it is available here. Likewise, assemble both the matrices so that we will get global stiffness matrix like this. Next, we will write the global equilibrium equation, that is Ku is equal to F. K is the global stiffness matrix, just now we found, into U, that is unknown nodal displacement vector U1, U2, U3, since there are three unknowns, and is equal to the point load vector. The point loads are there, F1, F2, F3. F1 is applied force at node 1. At node 1 there is no applied force given, write it as 0. At node 3 there is no applied force is given, write it as 0. And at node 2 there is applied force of P, that is 200 kilonewton. Hence I wrote 200 into 10 raised to 3 Newton. That is positive, I wrote, if the direction of load, if the direction of load is in the same direction of element numbering. If the direction of load, if it is in the same direction of element numbering, then it should be taken as positive. If the direction of load is opposite to the direction of element numbering, then it should be taken as negative. Since in this case the direction of load is in the same direction of element numbering, we will take positive, that is plus 200 10 raised to 3. Now once we get the global equilibrium equation, here three equations to be solved for U1, U2 and U3. Now there are three methods or approaches available in FEM to handle the boundary conditions. The boundary condition for this problem given is, at node 1 the displacement is 0, hence U1 is 0. At node 3 the displacement is 0, hence U3 is 0, because both the nodes are provided with supports. Now there are three methods to handle the boundary conditions in FEM: elimination method, penalty method, and multi-constraint method. Now we will solve these equations by applying elimination approach. What elimination approach says? If there are boundary conditions U1 and U3 both are 0, since these two nodes, node number 1 and node number 3 are provided with supports, eliminate first and third row and column. Eliminate first row, first column, third row, third column. Eliminate. Hence the remaining equations to be solved. If U1 and U3 are 0, if these are known, then no need to solve for U1 and U3, only you solve for U2. Okay, the remaining equation is, in the equation number 2, we have 10 raised to 4 outside. In equation number 2, that is, if you take minus 56 into u1, that is u1 is already 0, minus 30 into u3, it is also 0. Hence, directly you take 10 raised to 4 outside, that is 86 into u2 is equal to 200 into 10 raised to 3. Therefore, u2 is equal to, if you calculate, you will get for 0.2325 mm. This is the displacement at node 2, that is at the point of application of load, that is 0.2325 mm. Now u1 is 0 at node 1, the displacement is 0, at node 3 displacement is 0, and at node 2, that is at the point of application of load, the displacement we got after calculating 0.2325 mm. Now once we know the displacements at the nodes, now we can calculate the stresses in each element. Now let us go for calculation of stresses in each element. Stress in element 1. What would be the stress in element 1? We know that using Hooke's law. By Hooke's law, stress is given by Young's modulus into strain. Now stress in element 1 is given by Young's modulus of element 1, strain in element 1. What is the Young's modulus of element 1? Since element 1 is made up of aluminum material and Young's modulus is 70 GPa, it is given 70 into 10 raised to 3 into what is the strain? Strain in element 1, that is change in displacement divided by original length of the element 1, L1. What is change in displacement? Since element 1 is consisting of two nodes 1 and 2, that is final node is 2, initial node is 1, u2 minus u1 divided by L1. Therefore this is equal to 70 into 10 raised to 3 into bracket, what is u2? 0.2325, just now we have calculated, minus u1 is 0 divided by the length of the element 1, that is 300, already it is given. Now sigma 1, the stress in element 1, we got after calculation 54.25 Newton per mm square, that is in the bracket I wrote T, that means tensile. That is tensile stress of 54.25 Newton per mm square is induced in the element 1. Likewise, now we compute the stress in element 2 the same way. Sigma 2, that is E2 into strain in element 2, E2, that is Young's modulus of the element 2, that is steel material, 200 into 10 raised to 3, it is given 200 GPa, 210 raised to 3, that is megapascal, into strain in element 2, that is change in displacement by original length. Change in displacement for element 2 is given by final node is 3 and initial node is 2, u3 minus u2 divided by L2, length of the element 2. Okay, now proceed to the next page. Okay, in this, stress in element 2 can be calculated as Young's modulus of element 2, it is given, and u3 minus u2 by L2, u3 is 0 because it is provided with support, and u2 we have calculated, we got 0.2325 divided by element 2 length, it is 400. Now after calculation we got stress in element 2 as minus 116.25 Newton per mm square, since it is compressive in nature. That is, compressive stress of 116.25 Newton per mm square is induced in element 2. Okay, let us calculate the support reactions. Using elimination approach, support reactions can be calculated as support reaction is equal to internal force minus external force, that is Ku minus F. Since reaction force exists at node 1 and node 3, because the supports are provided at nodes 1 and 3, Let us calculate the support reactions at 1 and 3. For that, consider the equation number 1 of the overall equilibrium equation to calculate R1. In overall equilibrium equation, that is nothing but Ku is equal to F here, that is overall equilibrium equation. In this, you use the first equation for calculation, Ku minus F. It will give you R1 value, and Ku minus F third equation if you use, that will give you R3 value. Okay. Now R1 equals to 10 raised to 4 10 raised to 4 56 u1 minus 56 u2 plus 0 minus 0. What is this? Minus f1. F1 is already 0. Now we got R1 10 raised to 4 minus 56 u2. R1 we got minus 1,30,200 Newton. That is reaction force at support 1, left side support. Next R3. Considering equation number 3 of the overall equilibrium equation, we got 10 raised to 4 into 0 into u1 minus 30 into u2 plus 30 into u3 minus the f3, that is Ku minus F. F3 we have 0, that is also 0. Next R3 we got 10 raised to 4 minus 30 into 0.2325. How much you got R3? 69,750 Newton minus. Okay, now we got support reactions at node 1 minus 1,30,200, at node 3 minus 69,750 Newton. If you add these two support reactions, approximately it is 2 lakh, that is 200 kilonewton. Since the applied force is 200 kilonewton, hence obviously the support reactions would be 200 kilonewton only. This is what the elimination approach can be applied to determine the unknown nodal displacements, stresses in each element, and the support reactions using finite element method. In the next video session, I will explain you about the penalty approach of handling boundary conditions. Thank you.